BKW Physics. I'm Mr. McConnelly, and we're going to talk about total internal reflection. It's not something that a lot of people know before they take physics class, but it's a very, very useful property, and especially with the fiber optics that I talked about the other day, and I'll come back to that in a minute. So basically, here's what's going on. If you have a chunk of material, we'll say this material could be glass or plastic. And normally, when we were doing Snell's Law the past few days, we were concerned about how the light entered into the glass material. And we were saying, okay, well, it came in at a certain angle to the normal, and then it slowed down and so it bent towards the normal. Well, now, we're not so interested in how it got in there. However this light ray got in there, whatever. Now I'm interested in how this light ray leave into black glass. So I've drawn, for example, this black line, which represents a ray of light. And it comes down and it hits the glass-air interface. And when it does that, of course, now back to my typical ruler explanation that I've been showing you. The light waves are coming along. Which ones start to leave first? These. So what do? In this case, they speed up. So you can see that this bends away from the normal. Straight would be right there. It bends away from the normal. Makes sense to everybody, right? Well, let's take it to the extreme case. So if you continue to send the light in at a flatter and flatter angle, or a bigger angle from the normal, like say you take a light ray and you send it in here, where's it going to go? Well, it's going to speed up, right? It'll go maybe something like this. Take it a little bit further. If you send in a light ray like this, where's it going to go? Well, it actually reaches a point where it doesn't go into the air, and it doesn't really go into the glass either. It goes like that, like right along the surface. This point right here, well actually, this angle right here, the one I've drawn from the normal in the glass, is called the critical angle. And what happens at the critical angle is the light, when it goes to leave, it doesn't really leave. It follows the surface. So let me erase the blue and the black for a moment, because they kind of confuse the picture, but they helped you understand how I got there. So if we just look at that red one, we're at the critical angle right now because we came in, and boom, we went right along the surface. This is theta C, critical angle. What is the theta, like, we used to call this theta 1, right? It's the angle that you're, incident. What would you call this angle right here? Well, you would call it theta 2. What is the angle right there?
0.
Actually, from the normal, remember from the normal, always measure from the normal is 90 degrees. So that sets up where we're going with the equation. So we got sine n1 sine theta 1 equals n2 sine theta 2. I'm going to put all the n's on one side and the sines on the other side. So n2 over n1 sine theta 1 over sine theta 2. This was reference table. This is just me rearranging it. Now, what do we know? We know that this one right here, sine theta 2, is the sine of 90 degrees. And from your math background, what do you know about the sine of 90 degrees? It's a 1. So this, boom, is actually the number 1. So you have sine theta 1 is equal to n2 over n1. Or in other words, what we're calling this is the critical angle. So if you need to find the critical angle, you're going to take the n value of the, in this case, air, so in this case it would be 1, over the n value of this glass, which might be, in this case, 1.52. You're going to divide them, take the inverse sign, and it will tell you exactly what this critical angle is. Okay? So you can find the critical angle. But that says nothing about the title. The title is total internal reflection. I haven't even shown you that yet. So what total internal reflection actually is what if you found the critical angle, what if you go a hair further? I go down here now. Where's that light ray going? It's definitely not going out into the air because it didn't go out into the air before. It actually bounces right off the glass and never leaves. Total internal reflection. So basically, when you exceed the critical angle, you get total internal reflection, TIR. Total internal reflection. As soon as you exceed the critical angle, it'll bounce around inside. This property is the property that makes the cut of a diamond so important. If you go, guys, you go buy a diamond ring for a girl someday, or girls, you have a diamond ring someday, if it is cut correctly, you will get total internal reflection in the diamond. The light will go in, and instead of bouncing right back out, it'll bounce around inside based on the geometry of the way the diamond is set up. And then, what does that look like to you? It looks really shiny because the light is not leaving automatically, it's bouncing around, so it's like almost collecting light for a second, and it's going to look really bright to you. Back to the other example, the fiber optic cable. Remember I showed you that demo, and if you didn't watch that video, basically I took a laser beam and I shined it into a fiber optic cable, but the fiber optic cable was actually bent, and the light still came out the other end. The laser light came out the other end. How can that be possible? Now let's think about total internal reflection. If you shine the light beam in, and it's hitting at a very flat angle, which exceeds the critical angle, what are you going to get? Total internal reflection. And so you end up getting a scenario where the laser beam can't leave the fiber optic cable because it's always hitting it at an angle greater than the critical angle. Laser beam travels right through. Does that kind of make it clearer? Now they can enhance this too, because what they can do inside this piece of fiber optics is they can change the densities so that you have, let's see, higher towards the edges, you have a higher end value. In the middle of the fiber optic cable has a lower end value. This means not only do you have total internal reflection, but as you approach the edges, it'll start to curve because of refraction. So it'll start curving it, and then it will definitely hit at an angle bigger than the critical angle. Boom, bounces, and it continues on. And instead of, you're almost traveling at the speed of light. You're almost traveling at 3e8. Like if this is like a plastic material, you're traveling at 2e8. The light can travel very fast through a fiber optic cable. So before we cut this video off, let's try to see a visual of this. We're going to turn out the lights. We're going to get a glass block here. We're going to get a laser. And I'm going to try to show you the critical angle and total internal reflection. Is that a good spot?
Yep.
All right. So, first of all, if we just send light in, remember, we can show that light gets refracted, smells log, it's bent. That's no big deal. We've seen that a bunch of times. We can also do this. Like I can shine. Oh, I already exceeded the critical angle. Look at the bottom of the glass block. What do you see the laser doing? It's not actually leaving. It's hitting the bottom of the glass block and it's totally internally reflecting. So if I change this angle this way, it's just going to continue to do that. But if I go this way, I should reach a point here. I don't know. Oh, ooh, 2 total internal reflections. Look at that. I bounced it off the corner, and I'm actually going boom, boom. Alright, let's see if I can do it like this. Close, close. What I'm watching is, if you notice, the laser beam's coming in like this, and I'm watching how it's coming out the bottom. And if you notice, as I twist my angle here, starting to approach the point where it's not leaving the glass block. I'm getting real close. In fact, right about there, that angle that I just had, where it was coming in, it was almost traveling along the bottom of the glass. That was probably just about the critical angle. And then when I take it a tick further, it totally internally reflects and bounces around the inside of this. So for today,